time series analysis and forecasting. Introduction. Many decision-making applications depend on a forecast of some quantity. Here are several examples. Examples of forecasting applications. When a service organization, such as a fast food restaurant, plans its staffing over some time period, it must forecast the customer demand as a function of time. When a company plans its ordering or production schedule for a product it sells to the public, it must forecast the customer demand for this product so that it can stock appropriate quantities, neither too many nor too few. When an organization plans to invest in stocks, bonds, or other financial instruments, it typically attempts to forecast movements in stock price and interest rate. When government officials plan policies, they attempt to forecast movement in macroeconomic variables such as inflation, interest rates, and unemployment. Forecasting methods and overview. There are many forecasting methods available, and all practitioners have their favorites. The method can generally be divided into three groups. First, judgmental method. Second, extrapolation or time series methods. And third, econometric or causal methods. Extrapolation models. Extrapolation models are quantitative models that use past data of a time series variable and nothing else, except possibly time itself to forecast future values of the variables. All of these extrapolation models search for pattern in the historical series and then extrapolate this pattern into the future. The evidence in favor of simpler models is not accepted by everyone, particularly not those who have spent years investigating complex models. And complex models continue to be studied and used. Simpler models, on the other hand, track only the most basic underlying patterns and therefore can be more flexible and accurate in forecasting the future. Econometric models. Econometric models, also called causal or regression-based model, use regression to forecast a time series variable by using other explanatory time series variables. Several examples and problems in the previous two capture use time series data. The resulting regression equation has the form prediction from regression equation. This regression model might provide some useful result, but there are some issues that must be faced. Combining forecasts. There is one other general forecasting method that is worth mentioning. The forecasts that are combined can be the same general type extrapolation forecast, for example, or they can be different types, such as judgmental and extrapolation. The number of forecasts to combine and the width to use in combining them have been the subject of several research studies. There is not much evidence to suggest that the simplest way weighting each forecast equally, that is, averaging them, is any less accurate than more complex weighting same component of time series data. In Chapter 2, we discussed time series graph, a useful graphical way of displaying time series data. These components are called the trend component, the seasonal component, the cyclic component, and the random or noise component. This is a time series where every observation has the same value, because all observations in this time series are equal. The resulting time series graph is a horizontal line. We refer to this time series as the base series. We will now illustrate more interesting time series built from this base series. Measures of accuracy. We now introduce some notation and discuss aspects common to most forecasting methods. The forecast error is the difference between the actual value and the forecast. This double subscript notation is necessary to specify when the forecast is being made and which period is being forecast. There are actually two steps in any forecasting procedure. The first step is to build a model that fits the historical data well. The second step is to use this model to forecast the future. The most important of these are MAE, mean absolute error, RMSE, root mean square error, and MAPE, mean absolute percentage error. Here is the formulas. RMSE is similar to a standard deviation in that the error are squared. Because of the square root, it is in the same units as those of the forecast variable. The MAE is similar to the RMSE, except that absolute values of error are used instead of square error. The MAPE is probably the most easily understood measure because it does not depend on the unit of forecast variable. It is always staged as a percentage, testing for randomness. The fit value in this equation is the part calculated from past data and any other available information, such as the season of the year, and it is used as a forecast for Y. Typical forecast equation. For time series data, there is a residual for each historical period, that is, for each value of t. The point is that the fit value should include a component of the original series that can be possible be forecast, and the leftover residual should be unpredictable noise. The run test. We discussed two quantitative methods that tests for randomness. The first is called the run test. You first choose a base value, which could be the average value of the series, the median value, or even some other value. Then a run is defined as a consecutive series of observations that remain on one side of this base level. The run test is a formal test of the null hypothesis of randomness. If there are too many or too few runs in the series, the null hypothesis or randomness can be rejected.
Next is the random walk model. Random series are sometimes building blocks for other time series model. The model we now discuss, the random walk model, is an example of this. In a random walk model, the series itself is not random. However, its difference, that is, the change from one period to the next, are random. This type of behavior is typical of stock price data as well as various other time series data. That is the formula of random walk model, with where M for mean difference is a constant and T is a random series noise with mean 0 and a standard deviation that remains constant through time, and the other is a formula of one step ahead forecast for random walk model. 12.6 Moving average forecast. Perhaps the simplest and one of the most frequently used extrapolation model is the moving average model. To implement this model, you first choose a span, the number of terms in each moving average. A moving average is the average of the observation in the past few periods, where the number of terms in the average is the span. What span should you use? This requires some judgment. If you believe the ups and downs in the series are random noise, then you don't want future forecast to react too quickly to these ups and downs, and you should use a relatively large span. But if you want to track every little zigzag under the belief that each up or down is predictable, then you should use a smaller span. 12.7 Exponential smoothing forecast. Exponential smoothing is a method that addresses both of this criticism. It bases its forecast on a weighted average of past observations, with more weight on the more recent observations, and it requires very little data storage. There are many variations of exponential smoothing. Simple exponential smoothing is appropriate for a series with no pronounced trend or seasonality. Holt's method is appropriate for a series with trend but no seasonality. Winter's method is appropriate for a series with seasonality and possibly trend. 12.7a Simple exponential smoothing. We now examine simple exponential smoothing in some detail. We first introduce two new terms. Every exponential model has at least one smoothing constant, which is always a number between 0 and 1. Simple exponential smoothing has a single smoothing constant denoted by alpha. Its role is discussed shortly. The second new term is LT, called the level of the series at the time t. This value is not observable but can only be estimated. Essentially, it is an estimate of where the series would be at time t if there were no random noise. Then the simple exponential smoothing method is denoted by the following two equations, where ft plus k is the forecast of et plus k made at time t. There is the formula of simple exponential smoothing. Next is point 12.7b, Holt's model for trend. The simple exponential smoothing model generally works well if there is no obvious trend in the series. But if there is a trend, this method consistently lags behind it. For example, if the series is constantly increasing, simple exponential smoothing forecast will be consistently low. Holt's method rectifies this by dealing with trend explicitly. That is the formula for Holt's exponential smoothing method. 12.8 Seasonal model. So far, we have said practically nothing about seasonality. Seasonality is the consistent month-to-month or quarter-to-quarter differences that occur each year. It could also be the day-to-day differences that occur each week. In an adaptive seasonal model, an appropriate seasonal index is added to a base forecast. This indexes 1 for each season, typical average to 0. In a multiplicative seasonal model, a base forecast is multiplied by an appropriate seasonal index. This indexes 1 for each season, typically average to 1. 12HA Winter exponential smoothing model. We now turn to winter exponential smoothing model. It is very similar to Holt's model. It again has level and trend terms and corresponding smoothing constant alpha and beta, but it also has seasonal indexes and a corresponding smoothing constant gamma. This new smoothing constant controls how quickly the method reads to observe change and the seasonable pattern. If gamma is small, the method reads slowly. If it's large, the method reads more quickly. That is the formula for winter exponential smoothing model. Next, point 12HB. Deseasonalizing the ratio to moving average methods. You have probably seen references to time series data that have been deseasonalized. Websites often use the abbreviation SA and NSA for seasonally adjusted and non-seasonally adjusted. The reason why data are often published in the decentralized form is that readers can spot trend more easily. The decentralized and observation, assuming a multiplicative model of seasonality, divide it by the appropriate seasonal index. 12HC Estimating seasonality with regression. We now examine a regression approach to forecasting seasonal data that uses dummy variables for the seasons. Depending on how you write the regression equation, you can create either an additive or multiplicative seasonal model. As an example, suppose that the data are quarterly data with a possible linear trend, then you can create dummy variable key 1, key 2, and key 3 for the first three quarters, using quarter 4 as the reference quarter and estimate the additive equation forecast. This is the formula for this model, and then the coefficient of the dummy variables b1, b2, and b3 indicate how much each quarter differs from the reference quarter, quarter 4, and the coefficient b represents the trend. That's all of our presentation. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.